So the photoelectric effect, as you might guess, has to do with light, that's where the photo comes from, and some kind of charge, like the electron, that's where the electric stuff comes from. So the photoelectric effect, the main idea, is that you shine light on a metal, and if you do that, electrons can be emitted from the metal. That's the photoelectric effect. And that results in a positively charged metal, right? Because you have these electrons which have been ejected from the metal. So now the metal is left with more positive charges than negative charges. And this made sense to people. The electrons are bound to these positively charged nuclei in the metal. So without energy, without any extra energy, they'll just stay there. The electrons are attracted to the positively charged nuclei. But if you send in energy, like say through light waves, then they can get enough energy to leave. So you send in light waves, the electrons gain energy from those light waves, and they're able to escape. That all made sense, this photoelectric effect. You add energy to the metal by shining light on it, and the electrons will be ejected. Now in this view, you would expect that if you send in more energy, you will get higher energy electrons coming out, and you will probably also get more electrons coming out of the metal. That was the classical view. Send in more energy, you get higher energy electrons jumping out of the metal, and you get more of them coming out of the metal. So that leads us to Millikan's photoelectric experiment. In Millikan's photoelectric experiment, he had a setup where he was shining light on a metal plate to see this photoelectric effect. Now, across from this metal plate, he put another metal plate, and he set up a potential difference across the plates. So, if you shine light onto the metal, and if an electron is ejected from one of the plates, then it will be repelled by the opposite plate, right? Because you have this negatively charged particle coming out of a now positively charged plate, and if the opposite plate is negatively charged, then the electron will be repelled by it. Now, if the electron leaves its original plate with enough kinetic energy, then it may reach that oppositely charged plate. It may have enough kinetic energy to cross over to the negatively charged plate. If it does not have enough kinetic energy when it leaves the first plate, then it will not reach the other plate. It will be repelled, and it will probably return to its original plate. Now, if the electron has just the right amount of kinetic energy, just barely enough kinetic energy to reach the opposite plate, then we can set up a conservation of energy problem, right? And if we do that, we go through the steps, then we will see that the kinetic energy, that critical amount of kinetic energy, the just barely enough kinetic energy, is equal to the charge of an electron times the potential difference across the plates. So Millikan did this experiment, and he sent in monochromatic light. Now monochromatic, that means one color, and remember color corresponds to frequency of light also. So he was sending in one color of light, which is the same as saying one frequency of light. And what he noticed was that increasing the intensity of one frequency of light does not change the kinetic energy of an ejected electron. That is not expected. You would expect that if you increase the intensity of light, which is just another way of saying you're sending in more light, well, if you're sending in more light, you're sending more energy into the plate. And if you send more energy into the plate, wouldn't you expect more kinetic energy in those escaping electrons? But they didn't see that. Also, Millikan noticed that below a certain frequency, no electrons are emitted. So this frequency that's right in the middle is called a critical frequency. If you send in light that's below the critical frequency, no electrons are emitted. No matter how much intensity, no matter how much of this low frequency light you send in, you could send in a huge amount of energy. But if it's low frequency light that's going in, none of the electrons are ejected. Also, if you send in light above that critical frequency, even if you send in a small amount of energy, if it's above that critical frequency, some electrons will be emitted and make it to the opposite plate. Now, this could not be explained by classical physics. So it took Albert Einstein to come along in 1905, and he said that he could explain this, but only if you think of light as coming in bundles of energy. And these bundles of energy are called quanta. One bundle of energy is called a quantum. And one bundle of energy for light is called a photon. So a photon is one of these little bundles, these quanta of energy for light. He also said that the energy contained in one quantum of light, one photon, is equal to h times f, where h is Planck's constant. It's a number that was floating around in other areas of physics at the time. And it's equal to 6.63 times 10 to the minus 34 joule seconds. And f is the frequency of the light, the frequency of the photon. Then, if we think of it this way, each photon contains an energy equal to hf, so it can only deliver an amount of energy equal to hf if it interacts with an electron. So let's look back at this E equals hf. If you increase the frequency of the photon, increase the frequency of the light, you increase the energy contained in each photon. So high-frequency photons, the photons in high-frequency light, each contain more energy than the photons in low-frequency light. So when you increase the intensity of monochromatic light, you're not increasing the energy contained in each photon. The energy in each photon is determined only by the frequency of the light. When you increase the intensity, you're just making more photons. You're shooting more photons at the metal. And each photon just has the same amount of energy. It's just that now you have more of them. Let's see how this relates to Millikan's experiment. So in Millikan's experiment, he saw that below a critical frequency of light, no electrons are emitted from the metal. Einstein's model explains this. In Einstein's model, below the critical frequency, the photons do not have enough energy to knock the electrons out of the metal. Each electron has not enough energy to eject an electron. Above the critical frequency, each photon has enough energy to knock an electron out of the metal. And at higher and higher frequencies, those photons have more and more energy, and the photon is able to knock the electron out and provide more kinetic energy. So, at higher frequencies, the photons have greater energy, and so if a photon interacts with an electron, the electron gains much more energy, and it's able to escape the metal with much more kinetic energy. At lower, as we approach the critical frequency, those photons just have barely enough energy to knock the electrons out of the metal. And below the critical frequency, the photons do not have enough energy to knock the electrons out of the metal. In this model, we can set up an equation. We can say that the kinetic energy of the ejected electron is equal to the energy that was given to it by the photon, which is the energy of the photon, minus the energy that the electron has to use up in order to get out of the metal. So the kinetic energy of the electron when it leaves the metal is equal to the energy of the photon minus the energy that was lost in getting out. This energy that's lost, or that's used up by the electron just to get out of the metal, is called the work function, and it's represented by the Greek letter phi. Also, the energy of the photon is equal to h times f. Remember, E equals hf. So the kinetic energy of the electron when it leaves the metal is equal to hf minus phi. Or if we rearrange that, hf is equal to phi plus the kinetic energy of the electron when it's emitted by the metal. This is one of the equations that's given to you in the data booklet. Now, if the kinetic energy of the electron when it's emitted is equal to 0, in other words, if the electron just barely makes it out of the metal, then we get that 0 equals hf minus phi, or in other words, hf equals phi. So in this case, that frequency, when it just barely ejects the electron, that frequency is known as the critical frequency. So we'll call that Fc. So phi is equal to h times Fc Planck's constant times the critical frequency. And if we use that, we can use that expression, we can get that HF is equal to H times the critical frequency plus the kinetic energy of the electron. And the kinetic energy of the electron can be written as EVS, where Vs is the stopping potential, which is the potential across the plates in Millikan's experiment. And this gives us another equation that's given to you in your data booklet. So the takeaway here is that it's not enough to just think of light as a wave. That doesn't explain all of the phenomena that we observe. So for instance, in Millikan's experiment, we needed to think of light as acting like a particle in order to explain that. And that was Einstein's big contribution, or one of Einstein's big contributions. Now that doesn't mean that light is a particle. It also doesn't mean that light is a wave. Light is just light. All we're saying is that sometimes it behaves like our idea of a particle, and sometimes it behaves like our idea of a wave. Light doesn't have to behave like we want it to. Light behaves like light. It's just that sometimes that's like a wave, and sometimes that's like a particle. There's nothing mystical or magical or crazy about that. That's just what we observe.